distributions and normal plotting, 4 and 5 on my plan. Going towards data again a little bit. Back to data, back to a column in a data set. A column in a data set could look like this if you make a histogram. If it looks like this, for instance, that would reflect, for instance, an exponential distribution could look like this. If you had data actually coming from an exponential, it could also be a log normal maybe in a histogram like this. It's difficult to see the difference between a log normal and an exponential. That could look like this, both of them. Definitely this does not look like a normal distribution. Do we agree on this? A normal distribution should be a symmetric thing. So, to show the words I've given here, for many of the statistics that we're going to do, many of the tools that we're going to apply, they work best if data behaves like a normal distribution in the first place. At least then they work also nicely even for very small amounts of information, small amounts of samples. So that's why we have a little bit focus on trying to check and maybe try to do magic to make things look like normal distributions. When things look like normal distributions, a lot of the things that we do are okay. We are certain that things are okay. So sometimes we can transform something which doesn't appear to be normal. We can, by a simple trick, do a bit of magic and then maybe not make a perfect normal, but make something that at least looks much more like a normal than this one. And what we do is basically, for instance, not look at original data, but look at some nonlinear transformation of the original data. So it's like you may have a column in your Excel sheet with the X's, and then you maybe produce a new column next to it, and where you apply the log, for instance. That is the mostly applied transformation in statistics, the log transformation. Because the log transformation works like this. If you take these data, apply the log transformation, they will look like this. A log transformation makes bigger values smaller. So it's like applying the nonlinear log to all the numbers. That would only work if we have positive numbers. That was the situation that I showed you. There are different such potential transformations of data we can use. The log, as I told you already, is the mostly used. But there are others. And there are ways of trying to find out which to use, which goes beyond this course. I'm just going to show you that we can do it. And then we can try it sometimes and see if it helps us when we look at real data. What is the purpose of making the transformation? The purpose is to make something look more normal. So when we have a normal of something, it's because there is, I didn't do a very good job here, it's because maybe there is some kind of symmetric normal curve that fits the data that we have. That is to say that the data looks or comes from a normal distribution. That is repeating what I just said. It's nicer to do statistics on data coming from something that at least resembles a normal. So it's nice with a tool to investigate whether data looks as if it comes from a normal. To investigate this, we already saw a couple of tools into play. The most obvious tools to look, to investigate, to check whether data comes from a normal distribution is, of course, to make some simple plottings by histograms, as we just did, or maybe by box plots to see if the box plot is symmetric. That is a nice diagnostic tool for investigating whether data appears to be normal. However, there are more detailed, more elaborate approaches to actually make this comparison. And this is called the normal plot. And it has a formal definition and a formal approach of doing a normal plot. The idea of a normal plot, if I may jump back to my slide here. Let me try. That's not the way to do it. Sorry about this. Actually, let me try to put in a better normal curve here. That's a better, I just threw this in by hand. This was a better normal curve, I believe. Now the thing is, we could take the data points as they are shown in a histogram. And then in a way, at least I'm talking in principle here, we could compare the histogram with the, let me see, we could compare the histogram point with a normal curve point, right? We have a histogram point and a normal curve. These are almost on top of each other. This one, there's a difference between the histogram and the normal curve. Histogram, normal, histogram, normal, histogram, normal, histogram, normal, histogram, normal. At least that would be one choice then. I mean, to somehow compare, if we could turn these into some kind of plot where we have the normal here, and we have the data coming from the histogram, and then we could sort of make a scatter plot of what comes from the histogram and what comes from the curve to see if it's on a line. If it's on a line, it's because the two things match each other. That's the principle of a normal plotting that I'm going to show to you. Actually, this could be achieved in two different ways. It could be achieved by turning to the x-axis or the y-axis. One is the PP plot, the other is the QQ plot. We're going to dig into the QQ plot, where we dig down to the x-axis and look at that version of the plot. I mean, conceptually, it's showing the same thing. So we are going to see the QQ plot. I am going to, for one time's sake, take a small example. I'm going to take an example from the book. It's a naive example. Let me see. Showing you that we have 4 data points. We have 4 data points. They are 67, 48, 76, and 81. So it's example, I don't have the pages here. It's from the announced section in the book on the normal plotting. I'm going to show, in a way it's ridiculous to make a normal plot based on 4 numbers. But I'm going to show it to you anyway to be explicit about how the plot is constructed. So it's a bit more easy to be explicit with 4 pieces of information than 100, right? Let us maybe just to tease you a little bit, go into R right away, and then try to say, let's take a normal sample of only 4 points from a standard normal, and let's do a QQ plot. There's a function for that, which is called, I believe, QQ norm. There it is. I mean, it makes a scatter plot of 4 points, where we, on the y-axis, have, what were the number in this case? On the y-axis, maybe I should call it y just to emphasize, like this. On the y-axis, I have the actual numbers, I have the observations. On the x-axis, I have what in R is called a theoretical quantiles, something from the normal distribution, right? On the y-axis, I have the histogram points. On the x-axis, I have something from the normal. What do I have from the normal? What are the sort of the proper quantiles, the proper things to compare with? Well, here's the thinking. The thinking of the book. The book and R thinks a bit different from each other here, but I'll tell you both. The thinking of the book, the formal definition would be that when I have 4 data points, how should they be positioned if they should somehow fit exactly with coming from the normal? That's the kind of the idea. Then, if I have 4 points, I would say 4 points split the whole space into 5 pieces, you could say. So to fit exactly with the normal, it should split the space in 5 with 5 equal pieces of 20% each, matching the probability mass of the normal distribution. That would be the optimal, the exact 4 positions in the normal distribution. Then you can say, which normal? Well, I use the standard normal to compare with. So I should find, this one is called 0.2 because the set in the book notation, the subscript is used for the right-hand side probability, and this would then in R be P norm, which is the left-hand probability, which would then be P norm 0.8, right? The point in the standard normal curve that has 80% to the left of it, right? These are the points, and then this would be set 0.4. This would be, I didn't do the drawing very nicely here, but this is then minus 0.4, and this is minus 0.2 like this, right? I go and find these, and then I simply do a plotting, and then I have the y here, and I have these numbers on the x normal, the normal values down here, and I would get, I don't do it exactly now, I have these 4 points. Don't you see it? Fair enough. This one, I think I shouldn't take it. It's like, again, it's like I'm acting like a child now. You don't like one thing, I'm going to smash everything. You know. Let's try not to behave like a child. Too much, just a little bit. I'm a man, we act like children. I think this one you can read, set 0.4 also. And then this one is minus 0.4, and this one is minus set 0.2, like this. I think these were the most critical ones in my writing here. Thank you for letting me remember that I should focus on my writing. I mean it, that was not a joke. How could we find those numbers? We could take Q norm 0.8. We could take Q norm, I could do it in a naive way like this without listing. Here are the numbers. The 4 numbers, minus 84 minus 25 plus 25 plus 84. And then we plot these 4 numbers, and we would get the normal plot. Actually, I told you, I warned you already. Look at what R gave us by using the built-in plotting, the QQ norm function, which automatically does it for us, everything. Look at this theoretical quantile. It goes below -1, and I claimed it should be minus 0.84. That's not the same, right? Actually, R is doing something slightly different. I gave you, so far here, the book definition of the normal plot. Actually, there are several choices here. There are different options in R you could use also for these choices. The book definition actually corresponds to, this is the book. The book definition corresponds to a choice where you, as the individual probabilities, use, if we want to be general here, I divided by n plus 1. N is 4, so n plus 1 is 5, so it's 1 out of 5, 2 out of 5, 3 out of 5, 4 out of 5, right? These are the 4 quantiles we should look at. Now, in R, the default choice would be to go for something which is I minus a half divided by n. Whoa, what the heck does that mean? In our case, it means, since we have 4 observations, the default choice says we should have 1/4 of the probability mass in the middle, and then we have, to make it match, we have 1/8 out in the 2 extremes. That's the alternative definition of fitting exactly with a normal. So I mean, both are okay. It's not like one is wrong and one is correct. And in this course, both are okay, right? It's just to explain to you, if we use this definition and then use these percentages, we get exactly what R is producing to us automatically, right? That's what is going on with doing a normal plot. Let's try it actually a bit more. Did you send me some data? Let me just check my plan. We move on.